little sample problem. So it says the numbers of peaks and the areas under them, that's the size of the peak, in the spectra for these alcohols is used to identify them. So it's explain why the HNMR spectrum of this compound has 4 peaks. Predict the ratio of the areas under the peaks. That's the height of the column. It's when it says areas under, it's converting a graph which is similar to this into straight lines, like I showed you. That's what it's saying. So let's draw this. Here's a condensed structural formula. Notice it has, this is CH3, and there's CH3 attached to this carbon with an H, which is attached to CH2, OH. How many unique hydrogen groups are present? 1, 2, 3, 4. Right? Do you see why those are all the groups we're talking about here? If we go through that stupid process, this is a hydrogen attached to a carbon, which is attached to, we could prove that those 4 groups are the unique hydrogens. So we would see 4 peaks. This one would have a height of 1. This one would have a height twice that of the first. This one would have a height of 1. This one would have a height of 6 times that of the first. Do you understand why? Of course, this one would be further from the reference, right? The question does not ask about that. It talks about the magnitude of the peaks, the relative numbers of them. Does that make sense? You sure? Deduce the structure of the alcohol whose HNMR spectrum has 2 peaks with areas of ratios 9. So there's 9 hydrogens to 1. Well, it's an alcohol, so what group do you know is present? Okay, so there's 1. The other 9, since there's only 2 peaks, what can you say about the other 9? They're identical. There it is. Do you see it? Do you understand why? Each of these 3, 3, 3, identical. So a peak of 9 and a peak of 1. Does that make sense? Yeah.
So for the first one, the ratio shows 1, 2, 2, 4.
Here?
Yeah.
For the number? 1, 2, 1, 6.
Okay.
Make sense?
Yeah.
Anybody else have a question on that one? Okay. Let me go back to our regularly scheduled broadcast here. Let's see. We're not going to do that one today. Maybe we will. Okay, so that's HNMR. It's fairly straightforward. When you do practice tests, it'll make sense. Okay? Any questions on HNMR? Okay. Let's go ahead and go forward. Atomic absorption spectroscopy. I'm going to make this as simple as I can. I don't want to take much more of your time. I'm going to make you guys look up this one. It says to describe. Oops. Come on, baby. Be nice. Have no fear. Waggles here. That was good, huh? This is a YouTube blooper reel. That's okay. So you need to know that part. It talks about these. I'm betting that this question's not going to be there. But you are responsible for knowing the parts of one of these. I don't care if you study that. It's probably not going to be there. Okay, atomic absorption spectroscopy. This is using the spectrophotometers. That's all it is. It's not the kind. It's not describing the kind we put the little test tubes with solution in. It's similar in function. This particular type does not use liquid solutions. It basically aerosolizes it, tough word to say. Basically makes it into fine mist, burns the crud out of it to make it into small, small pieces, like atoms at a time. And so it takes the sample, it atomizes it, makes it into these small atoms, basically, and works just like a spectrophotometer in that you determine which wavelength to use. You shine that wavelength through, and just like in the first slide of this sequence, some types will be absorbed, some types will not go through. And the detector will detect what gets through and what is absorbed just like the spectrophotometers. Okay? Now the part I do want to cover is the fact that this technique is going to allow you to make a graph of the light absorbed versus amount. Now you've seen this when we have down here molarity, and then we use something called the Beer-Lambert law. I'll put C for concentration. Remember, this is a constant. Can't do that little symbol. There we go. Good enough. Whatever. This is a constant right here. This is the concentration. This is absorbance. That is a direct relationship. This has the form of Y equals mx plus B. It should be, plus B should be, the y-intercept should be 0, because when there is 0 chemical, there should be 0 absorbance. Very, very basic idea. So using this technique, see this thing here? It says determine the concentration of a solution from a calibration curve. So if you remember doing the Bradford test, you had to make solutions of known concentration and plot them. You then added a trend line, which you were given an equation of y equals mx plus b. Remember this? And then, once you had your unknown, you would measure its absorbance and calculate the value of concentration at that point by substituting this absorbance into this equation and solving for C. That is a common test question on these exams. When you do the practice ones tonight, you will see that. It's on. I was looking at one of them earlier today. It shows a graph like this, and it says to determine the concentration or the amount present when the absorbance is this. You simply move across to the axis, to the line, and go down to the x-axis. Okay. You guys remember Beer's law? Do I need to teach you anything else about that? Okay. You guys are getting burnt out. I understand. I see it. I'm almost done. How many of you have done chromatography in class before? Okay. Chromatography. Chromatography, 2 parts that you need to know. Mobile phase, immobile phase. Just like the name says, the mobile phase moves, the immobile phase does not. So a story I told pre-IB Chem, I think, is a perfect analogy. And I'm not going to be able to draw it, but I'm going to say it to you. It'll be recorded for posterity's sake. So before I tell you the story, we typically use... I'll tell you the story first. Now, the principle here is that chromatography is used to separate material, chemicals, from a mixture. And if you're tough enough to stick it out for another 15 minutes after this, I'll show you how we use it with proteins. But basically, you have compounds in a mixture. Now, remember, compounds have different structure, different bonds, and this whole section is about determining structure and bonds and polarity. So chromatography takes advantage of the structure, of the polarity. So the concept, I'm demonstrating paper chromatography or thin layer chromatography here, but all types work very similarly. The concept is we're going to put samples of our mixture. I'll just put a dot here. And let's say that red dot I just placed on this piece of paper is a mixture of chemicals that I want to separate. And I'm going to use their chemical nature to separate them. The paper plays the role of the immobile phase. It's not going to move. And I'm going to dip the end of this paper, which contains a spot of my mixture. I'm going to dip it in a solvent. And that solvent is going to play the role of the mobile phase. The solvent will move up the paper by capillary action. Now, this chemical will not be separated if it does not dissolve into or is not carried by the solvent. So that's the first principle we need to understand. This chromatography issue, the mobile phase must carry the chemicals with them. And they will be separated as they move up this piece of paper because they have different sizes and different polarities. Let me explain. You guys know those big floaty chairs that you can sit in a swimming pool? They have maybe they have a cup holder in them. So imagine we're all hanging out and this is going to sound funny, we're all hanging out in a grass field, sitting in those floaty chairs. That's kind of odd, I know, but it'll make sense. So we're all sitting there hanging out. It's the only chairs we had. We're on a picnic. and I got done lecturing about chem, and let's take a break. So we're all sitting in these chairs. We got our little drinks here, non-alcoholic, of course. And the river, the San Joaquin River is, right up there. It's beautiful, idyllic scenery. Oh, it's beautiful. But we didn't know that there was a heat wave in the Sierra Nevada, so all the snow melted just like that. So as we're sitting there, no one notices the river behind us is beginning to rise. And the river comes over the edge of the bank and starts to wash towards us on this grassy field. And as it gets to us, I'm like, whoa, don't panic. We're in floaty chairs. So just hold on. So the river gets there, and we start to float. Do we move with the water? Yes. So we are being carried by the mobile phase. Okay? So here we go. Now, I have longer legs than all of you because I'm taller. So my legs are dangling down, dragging on the grass. The water's high enough to where most of you, Prombic, maybe you're still with me, our feet is dragging, our feet are dragging, I ain't no English major, our feet are dragging in the grass. The rest of you, your feet are just dangling in the water. So who's going to move faster towards the forest up there? The smaller groups, right? The people whose feet are not dragging. That is analogous to polarity. Compounds that are fairly polar would stick to the immobile phase and move more slowly. Do you understand? So Parambik and I would begin to be separated from the group. The smaller people would keep going. Now we're approaching a forest. Okay? And the forest, it's immobile. And just stick with it, okay? And the forest has trees which are fairly close together, maybe 3 feet or so. And so you guys begin to get there. Parambik and I are going to make it there eventually, but you smaller folks are getting there. And which of you will move through those barriers more quickly? The smallest of you. So in that case, the size of the molecule would determine what gets through. Do you understand? So the immobile phase works in both of those ways. Now we can choose a different immobile phase to isolate polarity and or size and or both. But our analogy works perfectly. If I'm stuck to the ground or scraping the ground, I'm moving more slowly. That's the polarity issue. If I'm moving through trees, the smallest of us can maneuver through them more quickly. How many of you have done DNA gel electrophoresis? That is size exclusion chromatography. That's all it is. You pour your auger. The higher the percentage of auger, remember what that does? They move more slowly. Or you can apply a higher voltage, make them move more quickly. But the higher percentage of auger is the trees closer together. So the bigger fragments will move even more slowly. And so when you do your DNA gels, when you have your control lane, the ones that move the furthest are the smallest. Remember? That's what chromatography is based upon. It's either polarity, or it's size, or it's both. Very simple. Now, the curriculum guide here talks about 3 different kinds. There's paper, thin layer, and I believe the third, column chromatography. But they all work on the same principles. Thin layer and paper are just like this. There's a solid media that you have to move through. Column chromatography, usually it's like a burette, and there are beads or filter paper or something in here, and you pour the liquid in the top, and it could be size exclusion, so the smaller ones get through faster. The beads could be coated with polar substances, so things that are similar in polarity would be attached to the beads. Different polarities would move through more quickly. But it's all the same principle. Size and or polarities to separate things moving through an immobile phase. Does that make sense to everybody? That's chromatography in a nutshell. And I think that's it. The rest of the drawings we used earlier, I'm going to go ahead and stop.